Okay, so in the next video we are learning how we use a Lax-Wendroff scheme for one-dimensional unsteady gas flow. So we start again with these equations are also called sometimes Euler equations. So this is continuity, momentum, and energy equation for a one-dimensional flow. And now it's written in this form, okay, in this conservative form, where we have the quantity U, and often this is called flux vector, and the source term on the right hand side. So the energy is CV times T. Sometimes this is total energy, sometimes this is internal energy. And then you have a friction term and the pressure term. And note that if U is known, then you can recover easily the primitive variables, that is density, velocity, and the internal energy. And there is one more equation, that is the equation of state. Okay, so now we are not dealing with any kind of characteristic equations, and we are not reformulating our equations in terms of characteristics, but we are trying to solve these equations directly. So this Lax-Wendroff method, which is named after, actually, Peter Lax is a Hungarian mathematician who is still alive. They came up with this really clever idea that we want to construct a second order scheme, okay? And as you remember, a second order scheme is, so for example, central differencing is a second order scheme. So if you have some kind of function, then you try to estimate the derivative at this point based on the two neighboring points. And what we do now is, I will try, yes. So what we'll do now is the following. We have here the temporal derivative, and the temporal derivative, if I wanted to have a second order scheme, then I need the flux vector at the half time level here. Because if I used this here as a flux vector, then in time I would be using a central difference scheme here. And also, spatially, this would be centered. So this essentially means that df over dx is computed at this point. Okay, so half time level from these 2 points, that would be centered in space. And if I use this point to update time, then it will be centered in time. Okay, so it will be a second order technique. But of course I don't know anything here, because these are the points, the grid points, where I'm storing my variables. So there will be a preliminary step which will allow us to estimate these points here. Okay, so this will be a two-step technique. First, we'll need to have an estimate. We'll have to compute everything at the red dots. So here, here, and here. And then the main step comes, which is essentially centered in time and centered in space. Okay, so here we go. How do I update for the half time level? I'm discretizing the same equation. So the temporal derivative is between this point and this point. And this point is simply the average of the neighboring points. Or if you like, this is a linear interpolation. So I make a linear interpolation from this point and this point to the u vector here. And then I am advancing with forward differencing. So this is delta t over 2, and this is this point minus this point over delta t over 2. The flux vectors are centered at the all-time level here. Okay, so this is a center difference at this point for the flux vector here, and then the source terms are averaged here. Okay, now at this stage I have the u vector at the new time level, and what I will need is the flux vector here. So there is a step here that from the u vector you have to recover rho, v, and e and build the flux vector at this point. Okay, and then the main step comes. That is essentially, as I said, I will try to decrease so that we also see the figure. Yes, that is this is the centered time here, and this is the centered space here, and again I take the average of the source terms. Okay, so this is what Lax-Wendroff technique is about. For the time step control, you need, as we already did, the CFL criteria. So basically you try to ensure that the information does not step over a cell, which is this formula here, and then you use a safety factor. As for the boundary conditions, I did not write anything because usually what I do is that I use the isentropic method of characteristics for boundary condition handling. This essentially means that at the two ends of the pipe, so at the two last intervals, so between the first and the second and the last and the previous last grid points, I'm neglecting both friction and heat exchange and whatever there is. But the advantage is that the isentropic method of characteristic is a very clever and physical way of handling boundary conditions. Okay, so it's fairly simple, it's fairly straightforward. Don't forget that this is a second order technique, and I've added some codes, a very simple solver which uses Lax-Wendroff technique. So essentially, there are a couple of things I would like you to see. So this is the main step here. I don't have source term in this code. So this is the main step. The new u vector is the old minus dt over dx, the right flux minus the left flux, which is this here, the right minus the left flux. Okay. Of course, these fluxes need to be computed. I will show you in a minute. And there are a couple of utility functions. For example, how you compute u from p rho vt, and then how you compute the primitive variables from u. Of course, you also need an equation of state, which is here. Okay, so I wrote it in a funny way. The first argument is either P or rho, because sometimes you need to compute the pressure from density and temperature, and sometimes you need the density from pressure and temperature. So there is a flag, and if this flag is P, then it assumes that the first argument is pressure, and it gives you the density. And if the flag is set to R, then you are assuming that this is density and you want to work out the pressure. So this is pretty basic. And then again, the important bit, so how you compute these fluxes is here. Okay, so this is where I'm recovering the old fluxes, and here is the Lax-Wendroff estimate of the flux. Again, I'm using the same function to compute the left and the right flux here. Okay, so you can download these codes. The source term is not included here. And also if you have shockwave, so if you start playing around with it, you'll see that if the pressure difference is high, that is this here, sorry, yes. So this, if you expand from 10 bars to 1 bar, this is a shock tube problem. So essentially this means that in your pipe you have a membrane, and the pressure before and after, so this is 10 bars, this is 1 bar, and then you have you suddenly punctuate this membrane, and then you will have an expansion wave coming in this direction and the shock wave going in this direction. And you'll see that as this is a finite volume or a finite difference technique, you have problems around the shock wave. It will oscillate, and very often we add artificial damping to cope with these shock waves, these oscillations. Okay, the artificial damping will be added to the lecture notes within a week or so. Okay, so this was the Lax-Wendroff technique, the main idea, and then I will come back briefly with the last lecture, which is about computing the sonic velocity.